Okay, so here is my dynamometer test. I'm going to walk through what it is and then I'm going to do a demonstration. So both these are my projects kind of working together. Starting here, I have the power electronics module from last year. It's as a half-bridge motor controller, just using a high side switch and freewheeling down through the bottom diode. This is my battery pack I made this year. Connected to my battery pack is my balancing circuit, the core of this year's project. I have 4 series connected cells, and so there are 4 circuits. This is my dead time controlled PWM controller, and then I have the signals parallel to daisy chained across all the circuits. These are my 4 transformers. This is this integrated current loop bus, or isolated AC balance bus, whatever you want to call it, on the side of the transformers. Here I have 2 microcontrollers. At Mega 328s, it's the Arduino Nano. And this side is just a simple potentiometer that's giving a PWM 10 kilohertz signal to my power electronics module. I'm enforcing a maximum minimum pulse width of 95% and 5% duty cycle to make sure that I don't have a ton of switching losses on the 2 extremes. This is a filter cap, and then on this side, this microcontroller is a measurement circuit measuring the voltages of all my series cells. Both of those are connected to my computer here, and I have a serial monitor, and I am monitoring the duty cycle, and then the timestamp and voltage, or the value from the ADC on every cell, and I'm putting that in a spreadsheet program, and then graphing the voltage of cells over time so you can see they stay balanced upon charge and discharge and when it's being used. This is my dynamometer right here. It has a really interesting motor right here. It's a wound stator motor, but it has a separately excited field and a series field. I'm running it in SEPX mode right now because it lets me do some region stuff for charging it if I wanted to. This is an AC induction motor I stole off of an air compressor. They have a Lovejoy connector in the inside, so it can make sure that all the vibration stuff is satisfactory. This is a switch for the AC motor, and then this dealie over here is a water electrolyte variac I made. So water doesn't conduct electricity, it's the ions in the water that permit electrons to flow. And so I have 2 contacts, one right there, and then one on the other side right here, and a tank of salt water. So I control the distance between the 2 plates when the electrolyte remains constant, and I control the flow through the AC motor, which controls the torque on my series motor, which lets me have this whole energy moving back and forth type of thing. So that is the setup. Oh, and over here I have my oscilloscope on the signal going to the power electronics module, gate drive circuits up here. They're IGBTs and diodes. Don't have a cooling mechanism on right now, I just have it setting up because I'm not running an extended test. Then I have my fluke meter here measuring battery current. Note on battery current, the current here is actually 3 amps less than what is going through the battery, because I'm not measuring the separately excited field, which takes about 3 to 3.2 amps, depending on how much load is on it. So that's the setup. I'm going to just do a quick demonstration of some of the graphs I got. Let me just clear that so I don't kill Eclipse. So it's 0 my current. How do I do it? There we go. And I'm going to turn on my AC dyno motor right there. Increase the load a bit. Come over here and then turn on my DC motor. You see about 16 amps DC. See the duty cycle right there. You can get some pretty intense current. My circuit breaker tripped there, so that tells me I had more than 20 amps AC. But that's the test.